So this is the detailed content of this lecture here. So we will also look at Newton's ring as well. Now, these are beautiful colored light patterns which I took these pictures, these top two pictures, after I've sprayed this oil-based insect spray on top of water in a water collection tank, and the sun was shining at an angle, and I saw these beautiful colors, and I decided to take those pictures and see how colorful they are. Basically, all these are the component colors of white light, and that's all the different colors are displayed basically because these are the constructive interference for that particular wavelength, for that particular thickness, and also at the angle that I'm viewing it. And so that's why we get all the colorful patterns. And you will also see these colorful patterns in bubbles, whereby these are soap bubbles with the sunlight shining, and then you against the sunlight, and you will see all these colored surface. Now the soap bubble has a thin layer. Likewise here, the oil is a very thin film. And even on the road, after the rain, when there's water on the surface, now because of oil slick on the surface due to exhaust from the vehicles, so you will also be able to see colored patterns as well. So let's go into the physics about how we produce these interference patterns. Okay, so let's look at a simple diagram where you have a substrate. For example, it may be glass, or it can even be air. And then we have a thin layer of film which is transparent with refractive index NF. And of course, here is air. So we have an incident beam 1. Okay, and it hits at point A. And this dashed line here will be the normal. So it will part of it will be reflected into beam 2, and part of it will be transmitted into the thin layer. And when it meets the interface with the substrate, it will be reflected. And then over here, it will split into a reflected beam and a transmitted beam. So it's transmitted out as beam 5. And over here, the reflected ray will then get reflected from this bottom surface. So there are multiple reflections here, but we're going to see later on that these dashed blue lines, blue beams here are of much lower irradiance in such a way that the major contribution, it will be sufficient enough for us to just take the first reflected beam and the second reflected beam to calculate the condition for constructive and destructive interference. Okay, so then in our calculation of the words, we will just focus around this region. Okay, so you will see that at this point where the beam split into transmitted and reflected beam, basically the amplitude of the incident beam is divided. So in this case, this thin dielectric film, which is transparent, basically is actually what we have here is amplitude division. So it can produce interference pattern from the reflected rays. So this is an example of amplitude division interferometer. So when they recombine as a beam 2 and 5, the fact that they both have traveled different distances, so there would be optical path difference between beam 2 and beam 5 when they get collected at point P through a condenser lens. And we also have to take into consideration if there are any relative phase shift due to reflection. So it will give us a constructive interference or destructive interference depending on what condition they meet. So then we will then have to calculate what would be the optical path difference between beam 2 and beam 5. So let's expand that circled region that I showed earlier on. So they split, the incident beams start to split here. So the path difference, well, we will, from point D here, where, from a point C here, where the reflected beam, the beam reflected from the bottom surface, when it emerges out from the top surface at that point there, you draw a perpendicular line because these are parallel rays going out. So from here onwards, they will be equal distance before they meet at point P. But the difference in path taken by beam 2 and beam 5 would actually be contributed by this distance here, which is N0 times AD. And for beam 5 here, it would have traveled a distance of AB, BC multiplied by the refractive index of the film. So therefore, the optical path difference, so we put aside the phase shift that results from reflection first, just look at the optical path difference. So we have NF into AB plus BC minus N0 multiplied by this distance AD. Now, because AB, they get the angle of reflection, the refracted angle is equals to the incident angle at point B here. So this distance and this distance will be the same. So we can write this as 2AB representing that. But we would like to write this expression in terms of the thickness of the film, in terms of NF, and in terms of the transmitted angle theta t here. So let's work out the relation. Now AC is actually equals to AG plus GC, which is equals to 2, here it should be AG, there should be a G here. Now if you look at AG, AG is actually equals to, if you take the tangent of theta t, you will have opposite AG over T, right? So AG will be T tangent theta T. And AC then would be equals to 2T tangent theta T. Now, AD on the other hand will be equals to, now this is a right angle triangle, so it will be AC sine theta I. And AC, we substitute with 2T tangent theta T, so we have this expression here. Then we consider Snell's law, which is the law of refraction, okay, at this point here, with N0 sine theta I equals to NF sine theta T. Okay, so in other words, now sine theta I would then be equals to NF or N0 sine theta T. So we substitute that for sine theta I here. We have this expression. So we write it out, expand it. So we have 2T NF. This is sine theta T over cos theta T. So that gives us sine theta T squared, or sine squared theta T divided by cos theta T. And then from that triangle AGB, okay, triangle AGB. Now cos theta T is equals to T divided by AB. That's why AB would then be equals to T divided by cos theta T. Okay, so now we have the expression for AD and AB which we can then substitute into this AB, AD here. We substitute back into that equation, the path difference equation. That will give us the optical path difference will be equals to NF 2t over cos theta t minus N0 2t NF over N0 sine squared theta t over cos theta t. This cancels off. We have a common term 2t NF over cos theta t into 1 minus sine squared theta t. And sine squared and using the trigonometric identity, this will be equals to cos squared theta t. So one of these term cancels off. We will then have 2t NF cos theta t. So therefore, we are now able to express the optical path difference being equal to 2t NF cos theta t. Very simple, isn't it? What if we want to write it in terms of theta I instead? Well, we use Snell's law again. So for sine theta t, it will be equal to N0 NF sine theta I, right? So now instead of and cos theta t would actually be 1 minus sine squared theta t using trigonometric identity, and you root it. Okay, and then for this one, you substitute with this term here. So you substitute N0 NF squared sine squared theta I. And from here, if you were to bring out the denominator, the NF and F can cancel. Then you have NF squared minus N0 squared sine squared theta I. So finally, the optical path difference between beam 2 and beam 5 would then be equal to 2t into NF squared minus N0 squared sine squared theta I, and you root this bracketed term. So that's written in terms of theta I as well as the refractive index of the thin film, as well as the refractive index of the medium in which the incident beam comes from, and also the thickness of the film. So now if you want to convert this path difference into phase difference, well, now the phase difference is related to the path difference through a factor k, which is the propagation constant or wave constant. So this is equal to 2 pi over lambda 0. Lambda 0 represents the wavelength in air. So substituting this, so we then multiply that. And besides that, now if you look at the beam, let me see, I have the diagram here, yeah. This reflection here is actually external reflection, so there would be a phase shift of pi. Here is an internal reflection. There will be no phase shift. So therefore, we are going to consider the case where three scenarios here, whereby there's a phase shift. Looking at the phase shift that will occur at the top surface, that's of beam 2, and what would the phase shift for beam 5, and what will be the net relative phase shift between beam 2 and beam 5. Now, there would be a pi if N0 is less than NF. So that introduces a pi or a lambda, a half wavelength. And if NF is less than NS, there will also be a pi shift, which means that this would not be internal reflection, but an external reflection. Then in that case, both of them undergo phase shift. So the relative phase shift between the two of them will be 0. But in the case where this is still maintained, but in this case, NF is larger than NS. Say, for example, NS is actually air and it's just a thin film here of maybe the soap bubble. In that case, this will be internal reflection. There will be no phase shift. So the relative phase shift between the two of them would be pi or lambda over 2. Now, if this one is larger than NF and NF is larger than NS, okay, so there'll be internal reflection here, so there will be no net relative phase shift between the two reflected beams 2 and 5. So we came up with expression for optical path difference. Now we'll need to add to that the relative phase shift that results due to reflection. So for constructive interference, well, the wavelength, they must be in phase. So the total path difference, total optical path, the total path difference that arise must be equal to m lambda, full integer of lambda for constructive interference, and for destructive interference, then it must be equals to an half odd. You have if this m is 0, you have half lambda, or you have 3/2 lambda, or you have so odd halves of lambda, I would say, yeah, odd multiples half of lambda in that sense. Okay, so here are the written out expressions for constructive and destructive interference. So these are all the conditions for constructive interference written out in detail for case A, case B, and case C. So you can read that in the notes. I will not go through that here. But for normal incidence, that is when theta I is equal to 0, so theta T would also be equal to 0. In that case, if you look at that, we have a cosine function, right? Then in that case, this is 0, so this will be 1, so it's 2t and f. So the optical path difference would be 2t and f. So correspondingly, the phase difference would then be 2 pi over lambda 0 2n ft. Substituting that there. So, and if you, for the case, if you take the example of the case B here, therefore the path, the phase difference, the total phase difference, we will then have to add a pi. This is due to the optical path difference, and this is due to the phase shift upon reflection. We'll look into one of the application using interference in dielectric films. What we would like to produce would be an anti-reflective coating on, for example, our glasses. So if we want it to be anti-reflection, so that would mean that we would like to have ray 2 and ray 5, when they reach P, they both disappear. So how do we do that? That's when we force them to undergo destructive interference, and that can be done. We're going to explain now. So we have the incident beam in air, so we have n0 equals to 1, and this light would have a wavelength, let's say it is a single wavelength, lambda 0, and it enters the film, and this film will have a refractive index of nf, and then this would be your glasses. So this will be the anti-reflective surface, this T here, this blue layer here of thickness T. So usually the refractive index of this is larger than this, and this will be larger than this. So in that case, it will be similar to case A that we looked at 2 slides ago, and there will be no relative phase shift between beams 2 and 5, so we only need to consider the optical path difference. Now let's consider normal incidence, whereby the incident angle is 0, so therefore the transmitted angle would also be 0. So and we also consider, let's take a film thickness equals to lambda f over 4, where lambda f will be the wavelength of light in the film. Then how would lambda f be related to lambda 0? Well, we know that the frequency of light is related to the speed in air with a wavelength in air, and that is also equal to the speed in the medium divided by the wavelength in the medium. And we also know that refractive index of the medium is given by C, the ratio C over V. So in that case, C over V will give you lambda 0 over lambda f. Therefore, an f lambda f would be equal to lambda 0. So let's start with the thickness lambda f over 4. So the optical path difference of beam 2 and beam 5 would then be equals to 2 nft. Remember, cosine theta is equals to 1 because theta t is actually 0 since we consider normal incidence. So therefore, t here is lambda f over 4, so that gives us lambda f over 2. Okay, there's a 2 factor here. So nf lambda f is actually equal to lambda 0, so that will be equal to lambda 0 over 2 effectively. And how would destructive interference occur? Well, if you look at this diagram here, we have the thickness of lambda of 4. So we have incident beam of lambda, then you get a phase shift and reflected beam R1 from the top layer. And then as it enters into the medium, then you get another reflection from the bottom layer, R2. But these two beams are out of phase, so they cancel each other. And then you still have the transmitted beam that is able to pass through into the glass. Yeah. So so what we want would be destructive interference occurring at lambda 0 and to a certain extent a little spread around lambda 0. And but then we have white light coming in. So in the end, you'll find that you will be able to cut off. Let's say we make this to somewhere in the mid range, which is about 550. Then you have a small little range here where we can cut off the intensity, the reflected light. But we will not be able to cut off that well on the UV range and the red range. That's why when glasses that has an anti-reflective coating will look purple, because we have the blue and the red reflection, whereas uncoated glasses, then you see the reflection is just white light. And here the extinction will be more effective if the amplitudes of the two reflected beam are equal. Actually, then you have really total destructive interference. Yeah. So for normal incidence, the reflection coefficient, which is actually the ratio of the reflected electric field to that of the incident electric field amplitude, is actually given by a ratio of 1 minus n divided by 1 plus n. I'm not going into the derivation to get this. You just take my word for it that it is given by this expression, where n here would be the relative index of the second medium to the first medium. So therefore, if we take the amplitudes of the electric field reflected from top and bottom surface to be equal, and it will assume the film to be non-absorbing, that will occur if their relative indices are equal, meaning that NF, meaning that NF, or in this case NL here, NF over N0 will be equals to NS over NF. Yeah. So in that case, NF will be equals to root of N0 and S. Now since N0 is 1, then we can then choose a suitable refractive index material with this suitable refractive index, which would be root of NS. Now take an example for white light. If you choose a film thickness of lambda f over 4, lambda 0 around 550, yeah, because that's the one that's most sensitive to the eye. And we assume NS to be 1.5 for glass lenses, then ideally NF should be about root of 1.5. That will give you 1.22, and the nearest practical film material would be magnesium fluoride, and that one has a refractive index of 1.38. Yeah, so but there are other means of getting a better refractive coating by doing multiple layers of the coating of different refractive index, so that we can extend the range of wavelength that will that will occur in that will give us destructive interference. Fringes of equal thickness, or we call them visual fringes. Now, if we have an extended light source and we let it be incident onto let the beam hits a beam splitter, so that here it will be reflected onto a wedge foam, and then it gets reflected from the top and the bottom surface of this foam, and the first and two, just like what we've discussed before, the reflected beam from the top and the bottom surface of this wedged foam will then be brought to the view of the observer. So this will pass through the beam splitter. Now in this case, we have formed a wedge, which means that here is 0 thickness and here is D thickness. Now if you look at this arrangement, we can make this from perhaps 2 microscopic slide, and we put a very thin wire at the other end, and over this end we let them touch each other. And the distance, I mean the thickness of this wedge will be increasing linearly. Roughly, if we were to take that this gradient, let's say this gradient to be d over this distance, full distance L here, then we will have the distance x, or rather the thickness t at the position x from this end of the wedge here, being equal to, now look at this expression here, being equal to the gradient d over L multiplied by x. So basically it becomes, the thickness here is a linear function of x. So t varies linearly. All right, then let's look at how we get the interference fringes, of which these fringes will then have equal thickness. Basically, it is actually because of this linear function here that we have this increment in optical path difference, which increases linearly. So that's why we will have section, which is a constructive interference, another equal thickness of the fringe, that is destructive interference, dark, bright, and they are of equal thickness. So for a film of varying of thickness t that varies as well. In this case, the optical path difference varies according to what we already have derived in the beginning of this lecture. So at fixed normal incidence, we can theta t can go to 0. So we have 1 here. So we find that the path difference will be 2 nft. So, and like I said, because this path difference then will then vary due to a linear function of x. So hence you will see fringes of equal thickness spread out over this direction. So these are called visual fringes. So constructive or destructive interference, it can be determined to occur at condition given by, now we still have to include this delta R, which comes about because of phase shift due to reflection. This would be the relative phase shift between the two beams, and it will, if this term here goes to m pi, m lambda, we have bright fringe. When it's m plus half lambda, it is dark fringe. Just simple. So t increases from 0 to t here, 0 to d. Okay, this is an air wedge. So this equation here will be satisfied over consecutive orders of m. And that's how you get a series of equally spaced, alternating bright and dark, virtual localized fringes. So that's what you're going to see. Now here is this wedge here is an internal reflection, here is an external reflection. So there's no phase shift here, but there would be a phase shift here. So there would be a relative phase shift of lambda over 2 between the purple and the blue reflected ray. And this method can be used to measure the film thickness that is deposited on the substrate, but we will be observing the edge of the film. So this film, let's say, has a thickness D. Okay, so we make an arrangement that actually looks like a Michelson interferometer. Basically, we have this light source, and the light beam is brought by this fiber, and it will be incident onto a beam splitter, whereby part of the amplitude will be reflected onto the arrangement here, and the other part will be transmitted to reach this mirror and gets reflected back, and then here it gets reflected and brought to your viewing microscope. And over here, this beam that was reflected at the beam splitter now will then fall onto the arrangement of the substrate, and is preferable to let it fall at the point where there is that change in thickness of the film. There's the film edge with the substrate, and then it gets reflected back. Now, this beam, if we were to move this mirror, if we were to rotate this mirror, then this mirror will be at this position. So we will have one of the beam coming to the viewing microscope here would be traveling from here to here and get reflected back. And then the other beam would be coming from here to here and get reflected back, and part of beam that this beam is not just a single line, but is a beam of certain spatial transverse extent. So part of it will be reflected from the substrate. So the light beam should cover the film edge here. So how are we going to measure the thickness D then? If you look at this, so if we move M away or nearer, then we can adjust this position, this virtual position M prime, yeah? And we can also tilt the mirror M so that this M prime will be just slightly not so parallel to this, so that it will form sort of a wedge. And when they are not precisely parallel, so we have the extent of the beam, and then forming coming back to the view, they would have gone through a different path difference at different position of the beam, and this is varying as the wedge film just now, and you will see piezo fringes. So here, yeah, you see the background here, you see the piezo fringes. In this case, it is an example of a trench, or rather a dip here. That's why you see the background, which is due to the beam that was reflected from here, and the other part that's reflected from the mirror. So that two beam then forms this interference pattern. And you see the discontinuity here. Basically, that is because of the edge here, and discontinuity is because of the edge here. So if you then follow one of the fringe, you can see that it has dropped so much. So the drop is measured as delta x here, and the fringe separation is measured as x. So how are we going to measure the thickness then? So let's look at the shift, this displacement shift here, the shift in the fringe of the two interference pattern here. It will correspond to the difference in the thickness of the air film at the point where they join here. Now let's see, at the film here, we consider normal incidence. Then we have 2n TF here, 2n TF plus, if there is any phase shift, equals to MF for constructive interference. Now, for the other part here, you have 2n TS plus delta R equals to MS. Now, here is air, so definitely this is refractive index higher. Refractive index is higher. So, anyway, both of these will have the same relative phase shift. This will be equal to this. So taking the difference, that will give us 2n Ts minus Tf will be equal to Ms minus lambda. Now Ms minus Mf is actually the shift in the fringe. And this will be the difference in the thickness. Okay, Ts minus Tf will give you then D. So from this one here, delta T is equals to D. And from here, we can then replace this with 2 and N, because it is in air, that is 1. So therefore, we have 2D equals to the shift of M multiplied by lambda. So the shift of M. So in this case, is like if you follow through, that's 1 M, 2, so there's a drop in 1, and about 2, there's a drop of about 2, there's a delta M is about 2. So of course, to be more accurate, then you measure it exactly. So you already know the lambda, which is the wavelength of the monochromatic light that you use to illuminate this arrangement. So you should be able to find D then. Now, increasing the thickness by lambda over 2 will change order of the fringe by 1. That is, the fringe pattern would translate by 1 whole fringe. So hence, the shift in the fringe of magnitude delta M would actually be delta X over M will give you delta M. Okay, so in other words, now our D just now, or D will be equals to delta M lambda over 2. Lambda over 2, delta M replaced by delta X over X. So if you measure the fringe spacing and then you measure the fringe shift, of course, you can determine the thickness of the film. And however, there is a problem though. Now, if you look at this, if we were not able to follow this fringe shift, let's say this is very abrupt, and suddenly you get this to be shifted. Let's say this is shifted by 2. Suddenly you get this one to match with this one in form of full line. So you can't really see the shift. So that would be a problem. How much of the delta M? You can't determine how much of delta M exists. So to solve that, instead of making a very sharp edge, make an edge which is slightly inclined, so that we can then trace the fringe 1 to 1, as in this picture here. We can trace this so that we can see the shift in the fringe on Newton's rings. And here we have the light source with a collimating lens producing parallel rays, hitting a beam splitter, and then this light will be part of them will be reflected, and it will then fall onto a plano-convex lens, whereby the curved surface is resting on an optical flat, and then it get reflected. So down here, there's an air wedge on this side as well as this side. Here is a 0 thickness. Here will be the thickness over here. And then they are collected up, they are reflected back up, pass through the beam splitter, and goes through the viewing microscope. Now, looking at the geometry of that plano lens, well, it's a spherical lens, so that forms part of a circle whereby the radius of curvature can be related to what we define here as some distances. For example, if we locate, because you're going to see fringe patterns, and at a particular fringe pattern, which is thickness Tm, So you will locate this distance, this thickness here as Tm, and this will be r minus Tm. So taking Pythagoras theorem, you have r squared equals to rm squared plus r minus Tm squared. So here will be the distance from the center of the fringe pattern to the part where you're considering. Okay, and you will get contours, equal thickness contours, especially if this surface is a perfect circle, or in other words, the surface is a perfectly spherical surface. So if there's any irregularities, then it will come out as a distortion to that circular fringes, concentric circles. Yeah, fringes that form concentric circles. Now, at the point of contact here, where thickness equals to 0, we have a internal reflection up here, and at the bottom, you have the external reflection. So there would result in a relative phase difference of lambda over 2 due to reflection. Okay, so let's look at the radius of the mth order. So this is what you're going to see. These are the Newton rings pattern. This is when you look at the light that's reflected from the optical flat and passing through that lens. And this would be if you were to view it at underneath the optical flat. Now, because there's no perfect cancellation for the transmitted beam, so that's why the contrast is not so good. And over here, come back to this. So just now we had how relating the radius of curvature to Rm and Tm. So expanding this, and you'll find that 2r Tm equals to r squared, Rm squared and Tm squared. That's why R will be equal to Rm squared plus Tm squared divided by 2Tm. Now, Rm can be measured. That is from the center to whatever fringe you're looking at. And then Tm, which we don't measure, but we can determine it. We can determine from the equation that gives a condition for dark and bright fringes for the fringes of equal thickness. And R, of course, can be separately measured. That is the radius of curvature of the spherical lens. Yeah. So that can be measured. So you can easily then determine the thickness here. And this is a problem, a quantitative example for Newton's ring. You can check out the notes, the lecture notes, and I would like you to try this on your own.